This is still from the 2005, 2006 ACT.
41, I didn't get right.
So we did 41.
Oh, we did?
Oh, no, we didn't. Sorry, we did 40. Okay, yeah, right. 41. Let's do that. A over 30 plus B over 105 is 7a plus 2b over x. And a, b, and x are integers greater than 1, then what must x be? All right, so this looks pretty intimidating. There is sort of some guidance, like in looking at the problem, it actually kind of helps you through it a little bit. I'll show you what I mean. So on the left side, we've got two fractions, and that's equal to one fraction. Notice on the left, we've got a and b in the numerator. On the right, we also have a and b in the numerator being added. So how do you turn one fraction into two? Sorry, how do you turn two fractions into one fraction?
You got to get the common denominator and then like add them.
Exactly. And there's actually some help over here in getting those common denominators, because look at the 7.
Oh, yeah.
If you multiply this by 2, you'll get 210. If you multiply this by 7, you'll also get 210.
Okay.
So if you do that on both sides, you get 7a over 210 plus 2b over 210, which is 7a plus 2b over 210. And so that tells you then if 7a plus 2b over 210 is 7a plus 2b over x, then what's x?
210.
Right. Yeah, so, like I said, there's sort of some guidance in the problem that sort of helps you through it. So the first thing, like noticing that there's two fractions on the left and one fraction on the right, your first thought should be, well, like, how do I, how do you do that? How do you turn two fractions into one? Common denominator, and then the 7 and the 2 really do a lot of work there to help figure that out.
Yeah.
All right, questions?
No.
All right, what's next?
Um, 45 I got right, but I think I might have just guessed.
Okay. In triangle ABC shown below, the measure of angle B is 41, the measure of angle C is 34, AB is 25. Which of the following is an expression for the length in units of BC? Okay, so all of that is marked on the diagram, so we really don't need any of this, right? We can just look at the diagram. Note, the law of sines states that for any triangle, the ratios of the sines of the interior angles to the lengths of the sides opposite those angles are equal. Interesting. So normally on the ACT, when they want you to use the law of sines, they actually give you the equation. And they did here, but they just did it in words. Do you know how to interpret that, like how to translate that into an equation? Or do you just remember what the law of sines is, maybe? The law of sines states that for any triangle, the ratios, okay, so when you see ratios, that's fractions, right?
Yeah.
The ratios of the sines of the interior angles, so let's say the sine of B, for example. So the ratio of the sine of B to the length of the opposite side. So the opposite side, we could label, if we call this side over here side B, and call this side A, and call this side C, then we could say sine of B over B. So that's the first part. The ratio of the sine of the interior angle to the length of the side opposite those angles are equal. So that is equal to the sine of A over A, which is also equal to the sine of C over C. So that's the law of sines. And they kind of explain it there. That's very hard to read if you don't already know what the law of sines is. It's pretty hard to to parse that, but hopefully that makes sense. And that is going to be super useful here, because if we look at sine of c over c and compare that to the sine of a over a, we can leave b out of it. That will give us, that's basically the sine of 34 over 25 equals the sine of a over x, if I call this x. So what is the sine? What is a though? Do we know what angle a is?
You can do 180 minus
Good.
95. Oh no, 75.
Yeah, so that leaves 105. So that gives us this equation, and in this equation, there's only one unknown, so we should be able to solve it. There's a couple ways to go about it. The way I like to do proportions is you flip both sides upside down, so you end up with x over sine of 105, because I want that x in the numerator instead of the denominator, and then just multiply both sides by sine 105, and you get x is 25 sine 105 over sine 34. And that you can just pop in your calculator, or actually we don't need to, because that is choice B.
All right, yeah, that makes sense.
Cool.
My next one was 46.
For I squared equals -1, 4 plus I quantity squared is what? All right, so the first part here, I squared is -1. That's just sort of the definition of I, right?
Yeah.
And what are your thoughts? Where should we go with this to start?
I guess you should do 4 plus I times 4 plus I.
Yeah, great.
And then do FOIL.
Yeah, exactly. I'm gonna type because handwriting is not as easy to read as my typing. So 4 plus I times 4 plus I, and then FOIL or distribute.
Mm-hmm.
FOIL is another one of those things that I sometimes rant about. That's like an overly narrow tool to use when distributing is perfectly fine. So
Yeah.
distribute the 4 to both parts, distribute the I to both parts, and then what's the result? So 4 times 4 is 16, 4 times I is 4I times 4 is 4I, and I times I is I squared. Now, I squared, as soon as we see that, we should put a little flag in your head, right? Because we know I squared is -1. So whenever you come across an I to any exponent, we're going to simplify it. We'll come back to that in a second, but for now, we can just collect like terms. So we get 16 plus 8I minus 1, because I squared is -1.
Oh, you froze for a sec.
Okay, sorry. So yeah, we collect like terms. 4I plus 4I is 8I. I squared is -1. So we get here 16 plus 8I is -1. Collect like terms again, and you get 15 plus 8I. So that's choice J.
All right.
Okay, any questions on how I got there?
No. Alrighty, no. Yeah, that makes sense.
Okay. Okay, so let me talk a little bit, as long as we're here, let's talk about I squared, or just I in general a little bit. So we know that I is the square root of -1, right? And I squared is -1. Right, with me so far, all that makes sense?
Yeah.
Easy. So then what about I to the third? what can we say about I to the third?
That it's 1, right? It would be 1.
So it would be I to the third is I squared times I. Right? So if I multiply -1 times I, I'll get negative I.
Oh, okay.
Or you could also call that negative square root of -1 if you like.
Yeah.
Let's go one more. So what happens when you go I to the fourth?
Would that be 1? Because it's like -1 squared.
Yes. Yeah. So yeah, since I squared is I to the fourth, that would be -1 squared, which is +1. Or another way to think about it, it's I to the third times I. So if you multiply -I by I, you'll get -I squared, which is -1 times -1, which is +1. So yeah, whichever way you get there, you get to this. And so then, because I to the fourth is 1, then what does I to the fifth have to be? So I to the fifth is just I to the fourth times I, right?
Oh, so then just I.
Just I. So then you kind of start the cycle over again. So then I to the sixth would be the same as I squared. I to the third is this, or I to the seventh is the same as I to the third, and I to the eighth is the same as I to the fourth. And that, so because there's a pattern there, so let me write that out real quick, what I just said. So I to the sixth is the same as I squared, which is -1. And I to the seventh is the same as I to the third. Let me put a background on this so we can see what we're doing. Same as I to the third, which is -I. Hold on. Okay, got it. Sorry, which is -1. And then I to the eighth is the same as I to the fourth, which is 1. Okay, so we have this pattern. And what's nice about this is then if you wanted to find, say, like I to the 52nd power or something crazy like that. So let's say I wanted to find I to the, let's say 55, I to 55. How would you do that, do you think? Can you figure out how to make that jump?
What I mean, wait.
So I to the fourth is 1, I to the eighth is 1, so I to the 12th is 1. So you count by fours, right? I to the 16 is 1, I to the 20th is 1. So every multiple of 4. So if we go all the way to I to the 52 is a multiple of 4, right? So I would say I to the 52 is 1. Then you can go from there. So then I to the 53 is I, and I to the 54 is -1, and therefore I to the 55 is -I.
All right, yeah.
So you just find the biggest multiple of 4 smaller than the number you're looking for, and then you count from there. Does that kind of make sense?
Yeah, it makes sense.
So you could jump to any number, right? So if you needed I to the 278, you would just be like, okay, well, what's the multiple for? It's just smaller than that. So that'd be 276, I guess. And then you would say, okay, well, it's 2 more than that. So it would be -1.
All right.
So that's how you can use that repeating pattern to jump ahead of the pattern and find any I you need. Questions on that?
No, that makes sense. Yeah.
Cool. All right. Where to next? 47?
52.
Okay. 52. In triangle ABD, shown below, C is on BD. The length of AD is 6. Sine of D is 0.8. Sine of D is 0.8. Okay, so we'll have to think about what that means. How many inches long is CD? Okay, how is that information, the sine of D being 0.8, how is that helpful? Or what does it even mean?
It would be like, I forget what sine is, but some side over side.
Good, yeah.
Yeah.
What's the little rhyme that you learned to help remember those ratios?
Oh, SOHCAHTOA. Yeah, yeah.
SOHCAHTOA. So
Okay,
what
so
does
it'd
that
be
mean?
opposite and hypotenuse.
Good. Okay, so sine is opposite over hypotenuse. That's the so. So in that triangle, what is the opposite and what is the hypotenuse from D?
Opposite is AC, line AC, and then hypotenuse is line AD.
Good. So this is H. Okay, so if the sine of D is 0.8, that means that O, I hate using O as a letter because it looks so much like 0, but O over H, which is 6, is 0.8. Make sense?
Yeah.
So multiply both sides by 6 and you get O is 4.8.
Mm-hmm.
Okay, so that's nice, but be careful. Don't pick that answer because that's not what we're looking for, right?
Mm-hmm.
That's AC. They didn't ask about AC. They asked about CD. And this is actually a good opportunity to point this out. Just be careful when right before you pick your answer that you reread, make sure you know what the question is, because that mistake is a super easy one to make. I see students make it all the time, where you get, you're working, you're halfway done with the problem and you get 4.8 and you aren't careful enough. You're like, oh, 4.8, there it is. And you stop there. So just look out for that. Just make sure you double check before you circle that you're actually answering the right question. So if we know 4.8 is AC, then how do we find CD, the side we're actually interested in?
You could do something. So what would it be? Sine. Wait, no. It would be the wait.
So trig's gonna be tricky because we don't know
Yeah.
any other trig here, or like we don't know the other cosine or tangent. And we don't know the angle. So we could do we could do an inverse trig function here to find actually what D is, the angle D, and then use that and cosine to find CD. I think that's kind of the roundabout way to get there. I would just use the Pythagorean theorem, right? Because we have a right triangle and we know two sides, so you can always use Pythagorean to find that third side.
Okay.
So what's the Pythagorean theorem in relation to this problem? How do we set that up?
4.8 plus 4.8 squared plus x squared for the question mark, and then equals 6 squared, so 36.
Right. So 36 minus 4.8 squared, and then take the square root of that. And if we whip out a calculator, H.
All right.
Questions on that?
No, that makes sense. Yeah.
Okay, great.
Okay. Next was uh 57, but I may have to go back to a couple because I think I kind of guessed on them.
Okay. When graphed in the standard XY coordinate plane, the lines x equals -3 and y equals x minus 3 intersect at what point? Okay, so there's a few ways we could do this. We could graph it, but that's going to be pretty inefficient. So what's a faster way to get at this answer? It's actually pretty fast. We can do this. This problem could take like 10 seconds.
Well, wait, so would you substitute?
Mm-hmm.
Okay,
What would you substitute?
x for -3 in the y equals equation.
Right. So this becomes y equals -3 minus 3. So y is -6. So
Got
y is -6. And what's x?
-3.
Right. So that's got to be this.
Okay.
Just for clarity, let's draw it just, I don't know, so we know what we're kind of doing here. So the first equation, x equals -3, that looks like this, a vertical line at -3, right?
Yeah.
Do you know why is it a vertical line?
Because there's no, wait, there's no y value. Like,
Yeah, so
there's no slope.
yeah, so the way I like to explain it is for no matter what y is, like this equation, y is unrestricted, right? But no matter what y is, x is always -3. So it's not moving left or right at all. So x is -3 here, x is -3 here, x is -3 here, and down here. So x is -3 at every point on the line, but y can be anything because it's entirely unrestricted by this equation. Good. So the other equation, y equals x minus 3, if we use kind of y equals mx plus b, it starts at -3, and then it goes up 1/1. So it looks something like this.
Mm-hmm.
So there's an intersection down here, and that's this point, -3, -6, we found where they intersect by asking the question, where will this line be, the green line, when x is -3? That's essentially what we did by making that substitution.
Yeah.
And the answer is it'll be down here at -6.
All right, yeah, it makes sense.
Yeah. I don't know. Does the graph help at all, or like, does the algebra make more sense already?
I think that the algebra makes sense, but the graph does like
Add a
help
little
map
more.
it out a little.
Yeah.
But like now that I got it, I'll be able to, because algebra is pretty easy.
Yeah, it is. Yeah. Okay. So you said you want to go back for a couple, you think?
Yes, I think that. Oh, 56. Let me think about what.
The graph of the equation h equals -a² plus bt plus c, which describes how the height h of a baseball changes over time, is shown below. If you alter only this equation's c term, which gives the height at time t equals 0, the alteration has an effect on which of the following? The h-intercept, the maximum value, the t-intercept. All right,
so I like understood why it would be the h-intercept and I think the maximum value of h, just because I didn't know why changed to like t-intercept.
Gotcha. So I'm going to try, see if I can draw the rest of this graph. Something like that. And something like that. Okay, so that's the whole parabola, or more of it, I guess. So when you change c, how does that transform the parabola?
The intercept of the y-axis kind of like goes up, so it goes.
So it shifts the whole parabola up.
Oh, okay. I thought that would just be like only that one kind of line going up, and then the rest staying unchanged in a way.
Yeah. So yeah, you're basically changing where it starts, and so that's also going to change how high it gets and where it ends.
Mm-hmm.
So yeah, it changes everything when you shift it up.
All right.
Why do you think it is that changing C has that? I don't know if the question makes any sense, really. It's not a super clear question. Like, how did I know that that is the transformation that would happen when I change C?
Because well, obviously, like, you know that the y-axis point goes up, and then I guess you just have to know that it would change the whole thing.
Yeah, okay, so you could definitely know it just by like knowing
Oh,
how.
or because of the equation, because it says for the whole thing plus c would change it.
Mhm.
Okay.
Yeah, so let's talk a little bit about transformations in general, not just for parabolas, but for all functions. So for any function, so if I pick any function and I call it f of x, take f of x here. If there's a few ways that you can change f of x, you could add something outside of it, right? So you could just add to the function. You could add something inside of it, like this. You could multiply the function, the whole thing, by some number. You could multiply the inside by something. Those are all the basic transfer. We can also like put it multiply by a negative outside, or we could put a negative inside. Okay, so these are the basic 6 transformations that you can apply to any function. So there's a way I like to think about how these work, like a little chart that I think is helpful. Well, let's start with this. First of all, when you add or subtract to a function, it's always a translation or a shift.
Mhm.
You remember that?
Yeah.
And so that's what we have here. Adding C is a translation, so it's going to just shift the equation. If you add outside, it'll go up or down. If you add inside, it'll go left or right.
Mm-hmm.
What about multiplication? What happens when you multiply? So these are a shift or a translation. We'll just call it a shift. So what happens when you multiply? What's that do?
I know that one of them like affects all the y values, like it like multiplies all the y values by that, right?
Yeah. So
Yeah.
graphically, that looks like a stretch.
Mm-hmm. Or condense.
Stretch or condense, right? You technically the mathy word for it is it's a dilation, but we can just call it a stretch. It's fine. And then, yeah, like you said, if you multiply outside, it'll be vertical, and if you multiply inside, it'll be horizontal. And notice with the shift, there's actually a parallel there. With the shift, when you add outside, it's vertical. When you add inside, it's horizontal. So there's sort of a pattern we're seeing where transformations outside the function produce a vertical change, and transformations inside the function produce a horizontal change.
Mm-hmm.
The same thing applies with these last two. So these create a reflection or a flip. And again, when you do the negative outside, it's going to reflect vertically, and when you do it inside, it'll reflect horizontally.
Okay.
So we can make like a little chart to, sorry, go ahead.
Would it be like for the reflection, it would be for the outside, it would be vertically, so over the x-axis, or?
Yeah.
Okay.
Yeah, top to bottom.
All right.
So if we do like a little chart, I can put all of this information that we just talked about on a chart. Let me grab everything we just said and move that in here. Let's see if I can get that to sort of fit. And so if we do inside, or we'll say outside first, is vertical and inside is always horizontal. Boy, I'm really cramming that in there. So this will be, outside would be an up or down, up positive, down negative. Inside is horizontal, but it also kind of goes the opposite way you'd expect. So this goes left and right, but adding actually goes left and subtracting goes right.
Yeah, because like, it has something to do with like you would, but does inside do that?
Yeah.
Oh, okay, never mind.
So the way I like to think about why that is if you think about it in terms of time, I think it makes more sense. So when you add 3, it makes everything happen sooner, right? If you think of it as like a timeline. So like it happens 3 seconds earlier in time. And so that's a left shift. Things are happening earlier.
Oh, okay.
So whatever the shape normally looks like the vertex, like it's reaching the top of the parabola, or a saddle point in a cubic function, or whatever noticeable features of the graph. When you multiply, you get that stretch happening, and you kind of get the same thing. So when you multiply, that vertical stretch makes it bigger, and if you were to divide, it makes it smaller. Does that make sense?
Okay. Yeah.
When you do it inside, it kind of does the same thing, but again, works the opposite way that you'd expect. So here, when you multiply, it makes it smaller. And when you divide, it makes it wider or longer. And again, if you think about it in terms of time, it helps. So if you're multiplying the inside, you could think of you're speeding it up. So everything happens faster, right? So that on the timeline, it takes less time to get through the function. And when you divide, you're slowing it down. So everything happens slower. So you're spreading the function out on the timeline.
All right, yeah.
So yeah, I think thinking about X or the inside in terms of time, I think makes these make more sense. Okay, so last one is reflection. And this one's pretty easy. If you multiply by -1, multiply or divide, it's the same. By -1, you're gonna flip it top to bottom. And then if you do it inside, it'll flip it left to right. And this is the only one where it doesn't work backwards, but only because like it's binary, right? You're flipping. So flipping left to right is the same as flipping right to left. So it really doesn't make any difference. So you're just getting a horizontal flip.
Okay.
So that's it. That's the little chart, I think. And what's nice about this is it works for every single function. These rules apply to linear functions, quadratic functions, cubic functions, absolute value functions, trig functions, right? In trig functions, they get different names. They're called amplitude and period and phase shift and all that stuff, but it's still the same thing. It's still these same rules. You could use those words instead and it would just as well apply. Yes, square roots, logarithms, literally every function, these same exact rules apply the same exact way. So if you can learn these, then that will really help in all kinds of problems.
Okay.
So back to the problem we were just looking at, when you change C you could think of as being added outside the function. So that's gonna be a vertical shift. So if you increase it, it will shift up. If you decrease it, it'll shift down. So this is an upshift or a downshift. And either way you shift it, you're going to be changing the starting height, the maximum, and the height. What do they call that? The t-intercept when it hits the ground. So all of those change when you change C.
Okay, yeah, that makes sense.
All right, sorry, that was a long tangent. Hopefully that was helpful.
No, yeah, that is. I'm gonna take a picture of that, I think, at some point and then save it.
Cool.
Graph.
You can probably find a way better version of that, like my hand-drawn mess, but But yeah, it's all there.
Okay.
Okay. What else? Anything else you wanted to go over?
Oh, 50.
The right triangle below, the measure of angle C is 90 degrees. AB is 5 units, CB is 2 units. What is the tangent of B? All right. What can you tell me? What do we need to know to answer this question?
I guess like that tangent is opposite over adjacent.
Good. So again, that SOHCAHTOA thing, we get tangent is opposite over adjacent. And what are opposite and adjacent in this problem? So we're looking at this angle B.
It would be AC and then is opposite, and then adjacent is CB.
So this is opposite, and then adjacent is always the other one that's not the hypotenuse.
Mhm.
So what is the opposite side? Do we know what that length is?
No, but you know what adjacent is.
Okay, good. Can we figure out the opposite length?
Yes.
How?
You would do.
It's a right triangle, and we're missing one side.
Oh, Pythag, yeah.
Yep. So 5 squared equals x squared plus 2 squared. So 25 minus 4 is 21. And so the square root of 21 is that missing side. So if that's the square root of 21, then what is tangent?
Square root 21 over 2.
Yeah, opposite over adjacent.
Okay.
Yeah, that's it.
Oh yeah, I think that's what I did.
Yeah, so most on the SAT, all you really need of trigonometry is SOHCAHTOA. That'll get you virtually every trig problem you come across. On the ACT, SOHCAHTOA will get you 75% of the trig problems.
Mhm.
So SOHCAHTOA is always where you should go first and think about. SOHCAHTOA, the Pythagorean Theorem, will really do most of the work for you for trig. Occasionally on the ACT, you almost never see this on the SAT, but on the ACT, you're way more likely to see a law of sines or law of cosines problem. So those are worth knowing, although usually on a law of sines, law of cosines problem, they'll give you the equation. Even, I mean, I don't remember seeing this one before where they give it to you in a paragraph form. It's very confusing, but yeah, if you're familiar with those two equations and SOHCAHTOA, that will do pretty much every trig problem on ACT, SAT. The only other things that might be important to know are like just kind of knowing what does amplitude mean, and how does that relate to the equation. Which the nice thing about that is if you know what we just went over with the transformations, that actually will give you everything you need to know about amplitude and period and phase shift. As long as the one thing you need to memorize is that there's 6 trig functions, right? Sine, cosine, secant, cosecant, tangent, cotangent. The first 4 of those all have a period of 2 pi, and then tangent and cotangent have a period of 1 pi. And if you know that, then you can use transformations to get the rest of the way to find any periods you might need to know.
Okay.
So that definitely could come up on an ACT question as well.
Yeah, I remember we did a problem on that, I think.
Yeah.
On a different test.